Hi everyone. Sorry for the late start a little bit today. We were having some technical difficulties, but thanks for joining our webinar today on strengthening Ceph resilience with xiNOR and OSNexus. I'm Lauren Grobe, Director of Marketing at OSNexus, and we'd like to thank you for joining us today. We're going to have two speakers today. We are still waiting on our speaker from xiNOR. That's their CEO, Dmitry Lievshitz. And then from OSNexus, here we have Steve Umbacher, who is the CEO and CTO. Before we get started, if at any point you have a question, just submit it at the bottom middle of your screen in the Q&A box, and we'll try to get to them as we go along through the presentation. So with that said, I will pass it off to Steve.
All right. Thanks, Lauren. Uh, yeah, today we're going to go over some techniques for boosting the durability of your Ceph cluster by using local RAID, using xiRAID from xiNOR. And it's great. Dimitri just joined us, so we're all set. Um, one of
Thanks,
the
Steven.
challenge, yeah, good to see you, Dimitri. The first thing I wanted to talk about is dealing with clusters where you've got multiple sites set up, or a multi-site deployment, or sometimes called a metro cluster or stretch cluster. If you've got three different sites, one of the most common ways to configure your storage for these is using a replica three. This puts a copy of the data in each of the three sites, and when you're under steady state, all the sites are healthy. When you lose a single drive, you're going to have the rebuild happen using a group of drives, three drives. You have two of them remaining, but those two copies are going to be in the other two sites. So you're going to end up using a lot of network bandwidth to go and do a repair of a single drive. When you have a site outage, you still have two copies in the other site. But what if you had that bad drive in site one when site three goes out? What that means is that site two has the last remaining copy for some of the data. So if you have a site outage plus one drive, you're actually down to no parity bits left for some portion of the data. And what we're going to talk about today is ways to eliminate that. How do you make it so that if you've got a site outage plus one drive that's bad, which is totally possible to do, right? You think about what the average failure rate of a drive is. It's about 1.5% of drives fail on an annualized basis. If you've got a cluster with 100 drives, that means you're going to lose one and a half, roughly two hard drives in that cluster every year. And so let's say you've got one bad drive in one of the sites, and then you had that site outage. This is a very real scenario, right? So this can very easily happen. And in the case of a Ceph cluster, if this happens, if you're in this scenario where you had a bad drive in site one, it's just doing its normal rebuild, but then you had a WAN link outage that disconnected site three, you're in this scenario and the cluster is going to stop, unfortunately. That's because the standard way to set up a Ceph cluster is to have a min size of two. That means out of every three copies of the data in replica three, you have to have two of them online. You want that because you never want to be running your cluster with no additional copies. If you only have a single copy and that gets corrupted, you'll lose data. You can adjust it to min size one in that kind of repair scenario, but you're kind of running into this interruption of service. So this is a very real scenario that you can run into, and you have to think about this when you're especially when you're designing these stretch clusters. And this is just a diagram kind of showing you that example. Site A is offline while it was doing a rebuild of this OSD. Now this OSD, when you combine it with its replica copy here, you're down to a single copy over on the other side. And so this portion of data can't be rebuilt, or rather, it can, but you're down to its that single copy. So you're under min size. The pool's going to stop to protect itself. So the solution is to use layers, and this is exactly what you see in the public cloud. And here we're going over a scenario where you've got the local RAID protection provided by xiNOR xiRAID. And you can also use other techniques or in combination with xiNOR for like your NVMe, you could be using like a Seagate Exos Protect for your hard drive storage. This gives you a local layer of durability in every single node so that if you lose a drive, that node can go and repair it. And then you do distributed erasure coding or replicas across the different sites. This is super important because now any drive failure is all going to be repaired locally. And the neat thing here is when you're doing a local RAID, it doesn't matter how many drives. If you could lose a single drive on every single node. If you're using double parity locally, you could lose 2 drives on every single node of your cluster and still have zero downtime and zero impact on the Ceph layer above it. So this technique takes the durability in it where you might have a durability of 6 nines or 7 nines for your Ceph cluster and 6 nines for your double parity local RAID. It combines these together and you end up with somewhere in the neighborhood of 12 to 14 nines, depending on the stripe length that you've configured. And this is what that looks like. So we're going through the same example where we've lost a site. In this example, we've lost like site C, but you can see you can lose a drive out of each one of these xiNOR RAID sets and still have zero downtime and zero impact to the Ceph cluster OSDs in site A and site B. So you still have your 2 replicas available on, in this case, using replica 3 with a erasure, or rather the local RAID underneath it. But this equally applies to using erasure coding techniques above just as much as it would for replica 3. But replica 3 is kind of a very easy example to go over. So yeah, now you're not stopped by one, and you're not only still not stopped by one, but in this case, because these 4 bad drives are in 4 different groups, you could lose all of those, and again, zero impact. So the durability super high versus the first example. And this is a technique that's been around for a long time. When you take a look at how the public clouds operate, they're all taking this kind of a technique of doing 2 layers. One thing I wanted to comment on is the LRC. This is the local reconstruction codes. This basically, this is like a 6+2 data erasure coding, and then you split the 6 chunks into 2 local groups so that you can do localized rebuild. But this kind of localized rebuild is for a site. So you might be using the network, you're going to still be using the network, you're still going to be using multiple nodes in one site to try to do that rebuild quickly. It does eliminate the WAN traffic, but you're still impacting the cluster. And so you don't have that independence of layers that you get when you combine a local RAID with a distributed parity. So this is significantly less durable than a double layer technique. A good example of a double layer technique is Wasabi. Here you can see they're using a 14.4 across the nodes and facilities, and then underneath they're using a local ZFS. But this double layer technique is just used pervasively across the industry. All your public cloud storage is using this kind of technique. And this is the thing, when you get to a larger scale, that's the other area where this technique is really critical. If you've got a cluster with thousands of hard drives and or flash devices, this is the clear way to go and get that extra durability and to basically operate your cluster just as a public cloud provider would. And that's kind of the one of the key scale points is right at around that area of around 1,000 drives plus or minus. You're going to really benefit from this style of technique. Or it can be much fewer drives, but a stretch cluster, and this technique is also going to pay a huge amount of benefits. So that's where kind of going through this technique. Basically, you're taking your local NVMe drives, combining them into the xiNOR xiRAID. So you've got that local durability on every single node. And within a node, you could even have separate groups, having multiple RAID groups. So you had 36 NVMe drives rather than putting them all into one. You could do like multiple groups in there, 3 groups of 12 as an example. These then produce logical drives, and you produce from those logical drives, the Ceph cluster is then layered over these logical devices coming out of the RAID group. And this is where you get into that neighborhood again of 11 to 14 nines, again, depending on how long the stripe lengths are. Um, so, kind of looking at those benefits in more detail, all 3 sites healthy. We've got full redundancy. This going back to that first example, 1 site offline, you're 1 disk failure away from IO suspension. But here, 1 site offline, you still have 2 full copies. And so you're ready to absorb disk failures even with that site outage. And then here's site offline plus that extra disk failure, no problem. Xinnor RAID's just completely absorbing that. 2 disk failures. This is if you've got Xinnor RAID set up at RAID 6 or higher, or you've got those failures across 2 different nodes, that's going to still get absorbed. And site offline with a drive failure, your recovery window here is going to be quite a bit longer with the time to recovery versus having everything completely protected and local rebuilds happening super fast with Xinnor RAID. More information here on just sort of the overhead. You do pay some amount of overhead having local RAID. So depending on what you select, as an example, an 8+2 would have a 20% additional overhead for your cluster. Using something longer, or going with a single parity locally, like an 8+1, can reduce that and give you 90% of your local storage or of the storage. So you multiply the two together. If you have distributed efficiency of 8+2 with erasure coding, and you've got 8+1 for the local RAID, you'd multiply those two together and you get 72% efficiency. So the efficiency still stays very high when you are combining these layers. And it's actually can be as efficient or more efficient than using the local reconstruction code, the LRC technique. This is a little bit on the integration that we've done. You can see inside a Quantastore when you go set up your Ceph cluster. Well, before that, you'd go in and set up the local RAID units, and you can do that all right through our web UI. You can click to go and create the RAID unit and then create the logical drives. So in this example, these 4 NVMe drives were turned into a series of 6 logical drives so that we could use those within the Ceph cluster. But you'd have this on every single node, and then now you've got this local durability across each of the nodes. And the neat thing with xiRAID is it's all software, and Dimitri's going to dive into that next. So here I'm going to pass the baton to Dimitri to dive into kind of the limits of some of the legacy techniques for doing local RAID.
Okay, thank you, Stephen. Okay, so RAID is not something new in the market. There are a lot of RAID implementation which are available on the market decades from now. So what's the problem with traditional RAID implementation? Typical RAID implementation is the hardware RAID card. Hardware RAID card, great solution for HDD. What is wrong if you use hardware RAID card for NVMe? First of all, by design, hardware RAID card, it's a RAID card with 16 PCIe lanes. So even in theory, you could serve maximum 4 NVMe drives. I would like to remind you that each NVMe drive is connected by 4 PCIe lanes. So even in theory, if you use hardware RAID cards, you could just serve maximum of 4 NVMe drives. In reality, you wouldn't get even performance of the 4 drives. What is wrong as well with hardware RAID cards? It's PCIe slot taxation, because in this case you need to use PCIe slot for RAID calculations instead of expose network using this PCIe slot. And what we see in all modern infrastructures, that the biggest challenge is how to expose all the network to feed GPUs, to feed compute nodes, to make it maximum effective for end customer implementations. So hardware RAID has its own limitation. What else? For sure, you could look on some solutions which is called GPU assisted RAIDs. This case, it works a bit differently than hardware RAID. It's parity calculation offloading on GPUs. In theory, if you are in a normal RAID operation, you could serve more than 4 drives and get a performance for more than 4 drives. But in case if you are in rebuild or degraded mode, with GPU assisted RAID, you have the same problems of PCI slot taxation and 16 PCI lanes that you could just serve 4 drives and that's it. And everybody knows that you need RAID, not in case when everything is going smoothly. You really need RAID data protection if something going wrong. And this case, you need that all rebuild operation would be executed as soon as possible. And as Steven told, it's a matter of surveillance of the data in large-scale Ceph installations. So this case, GPU assisted RAID, it's not the best solution available for large-scale installation today. For one server, it may be okay. For large-scale deployment like Ceph deployment, for sure it's not okay. The other alternative, software RAID, it's not something new that comes to the market with us. There were a lot of open source implementation. The most popular one is MD-RAID. And everybody who uses MD-RAID understands that MD-RAID it's a great solution in case if you don't need to get good performance. You can get decent performance with MD-RAID in sequential read workloads as soon as you are in write workloads, especially in random writes. And as well, as soon as you are in rebuild mode, in degraded mode, then with MD-RAID you couldn't get great performance because it's designed in a way that you have spike of loads for some CPU cores in case when other CPU cores are idle. And this case, it's a problem to get maximum possible performance you can get out of your NVMe drives. So we address exactly this problem. We solve data protection problem for NVMe by our technology, which is based on 2 cornerstones. First, what we do differently than all the other guys, it's our patented way how we do RAID calculation itself. So we do our own way of data placement and our own way how we can do parity calculation. And by the way, it's equally effective to all RAID levels. So it's not only about XOR in RAID 5. It's as well the same for RAID 6 and even for RAID N plus M. Because what we support, it's a RAID group with up to 64 drives in every RAID group. And you could use up to 32 drives for parity in one RAID groups. For sure, in Ceph installation, it's not needed, and practically speaking, RAID 6 is more than enough for most part of the Ceph installation. But as well, if you have, say, nodes with 24 drives in one node, as we see in several customers in our cases, maybe you need more than RAID 6. We call this RAID level RAID 7.3 when you use 3 drives for parity. In this case, your RAID penalties in RAID 7.3, it's more or less the same as RAID penalty in RAID 6. So it's about our way how we do parity calculation. The second cornerstone of our solution is our data path, which is specially designed for NVMe for PCI Gen 5 and further PCI Gen 6. Here we have 2 flavors of our implementation. One flavor is what was used in our joint solution with QuantaStore called xiRAID Classic. This case, local node level protection provided by kernel space driver implements our software. The second flavor of our product is a user space data protection engine, where we provide not only local data protection, but as well we provide distributed erasure coding, as well as distributed NVMe over Fabric support in both target and initiator side. Would it be relevant for future Ceph installation? Probably yes. For most complicated cases, it would be possible as well to use not only local node data protection by our software, but as well to use distributed erasure coding for more interesting cases. Yeah, let's look on some benchmarks. We compare our xiRAID Classic, as I told, it's our kernel mode implementation with MD-RAID and Broadcom MegaRAID. And when we compare our implementation with MD-RAID, we do comparison with MD-RAID 10. Why? Because if you compare with MD-RAID on a parity rate, then you would get even worse numbers from MD-RAID. And for MD-RAID 10, you as well pay capacity price for data protection, because this way you should double your capacity just for data protection. So you can see that in sequential read results are comparable. In sequential write we provide almost 2 times better performance than MD-RAID in RAID 10, and in our case it was RAID 5. For random operation, you could see that numbers said by itself, so we are much more better in both random read and random write workloads. And it's true not only for Broadcom specific implementation of MegaRAID, it's as well absolutely the same numbers we saw with Dell PERC adapters, because it's as well the same limitation of hardware RAID as it is for Broadcom adapters. So
yeah. The MegaRAID is rebranded, right? When you see the Dell PERC controllers, their RAID controllers are a rebranded version of the MegaRAID, as I understand.
Yeah, absolutely, Stephen.
And this really gets to the choke point that you were pointing out earlier. You know, with the hardware RAID, it's really crushes the performance here. The MegaRAID's really suffering here at just 28 gigabytes per second versus 300. You know, just it kind of shows why hardware RAID just doesn't work anymore for NVMe drives.
Yeah, absolutely. Okay, so let's talk a bit about rebuild. Why rebuild is important? Because you need data protection in cases when something goes wrong. So what we did? We did the joint study with Solidigm, where we try to understand how our technology impacts on QLC drives rebuild time. So we did the following experiment. We use RAID 5 over 9 NVMe drives, so it was RAID 8 plus 1. And we look what would be with rebuild time in case if you lose one drive in RAID 5. And simultaneously, for sure, during rebuild, you should use the normal workloads on a RAID array because you couldn't just have rebuild when you don't have any I/O in real life. So this case, you could see that rebuild for us takes a bit more than 50 hours. Extrapolation for MD RAID shows that it's more than 60 days. For sure, we didn't wait 60 days. It's extrapolation of our test out of 2 weeks. What is even more important than absolute rebuild time, it's a workload that you could observe during your normal I/O operation in degraded mode. With us, it's great numbers, which are more than 40 gigabytes per second in read and 13 gigabytes per second in write. With MD RAID, you could see 2 magnitude of order worse results. So it's just 100 megabytes per second. It's even not measured in gigabytes. And the last but not least, it's about write amplification factor. Because when you keep up with QLC installations, then write amplifications matter the most because you need to use your drive as long as possible. And in this case, we significantly decrease write amplification thanks to the architecture of our metadata and data placement.
Yeah, and I wanted to just add here, this 53 hours is quite fast, especially for a 61 terabyte drive. And the other thing I wanted to add is this, this is 30 times faster roughly between just a traditional MD RAID, software RAID, which again is much faster than using the hardware RAID. But that 30x turns your say you're calculating that expecting 6 nines of durability out of your RAID layer. That number of nines goes down to 5 and 4 nines depending on the rebuild time. That rebuild time is absolutely critical for calculating the overall durability of your cluster. There's various programs online where you can do the Markov chain analysis to put in the 2 layers, and it'll calculate out what your overall cluster durability is. But this is a real killer. The probability that you have another failure within that 67-day window, which is massive, is quite high versus a small window like 2 days in this example. So yeah, this is a huge factor when you're calculating your cluster durability. Yeah, this is great. Yeah, thanks, Dmitry. Go ahead.
Yeah, technology that we developed use in scale for large installation today. So let's look on our IO 500 deployment, which was done in Erlangen National High Performance Computing Center at Germany. It's one of the biggest AI supercomputing center at Europe. So we managed to be on a podium of IO 500 out of all deployment in production. So it's not tests, it's production deployment. And we managed to demonstrate that we can significantly accelerate Lustre and be the fastest Lustre installation worldwide. For sure, the same stuff that we demonstrate with Lustre, we can demonstrate with Ceph. And thanks to the integration which was done by OSNexus, we demonstrate that exactly such type of the deployments applicable for Ceph.
Yeah, this is really great proof, kind of showing how xiRAID's accelerating really any file system and just as easily Lustre in that world-class file system high performance computing environment as it can for accelerating a Ceph cluster. So kind of the key takeaways. The dual layer erasure coding is just the industry standard for public cloud. It's not a luxury. It's really a must-have when you start getting into greater scale or a multi-site deployment. So it's just everywhere, and this is a great technique for applying that locally to your Ceph clusters. Compound failure scenario that we were talking about in the beginning is just really not a corner case. Whenever you're designing your Ceph cluster, you want to say, okay, this is what I'm expecting. I could have this rack outage, I could have a site outage, depending on what you're designing for, the scale that you're designing for. You need to take into account what happens when that outage takes place, plus another failure, whether that's another drive or another server. That tells you what the true durability of your cluster needs, and you need to design into that techniques like this where you're using 2 layers or more parity bits. But the 2 layers gives huge benefits to Ceph because when you have a drive failure, the Ceph cluster is not impacted at all. You don't have peering going on. You don't have that temporary stun. All those things go away when you have a layer underneath it that's providing durability so that it can absorb and rebuild from a failed drive super quickly with zero network load, right? Especially when the network is super precious, whether that's because you've got these primary workloads that need the performance, or you've got a wide area network, distributed cluster, whether that's across different buildings on campus or across different campuses. Having local RAID makes a massive difference because again, a bad drive rebuilt itself within hours, right within the server where the drive failed. And then the last bit, we've done a lot of work together, xiNor and an OSNexus, to integrate xiRAID directly into Quantistore. So you're able to go and set up your RAID groups right within the web UI, and then immediately go to set up your Ceph cluster and with a few clicks, you're up and running and your cluster's operational. Really within a couple of hours, including all the network port configuration and other things, which you can also do all right through the web UI. That's all the key things we wanted to go over. Lauren, any questions there? Looks like we don't have any questions so far.
Yeah, there was one that came in. Does this solution change how you size your clusters for capacity?
Yeah, whenever you you want to design to figure out, okay, what is my overhead for the Ceph layer first? So let's say you've got a cluster and it's got 1 PB and you're doing an 8+2 over that with Ceph. That means you're going to get 80% usable there. And then when you calculate the xiRAID underneath, as an example, say you're doing 8+2 at that layer as well, that's going to give you 80% usable. So you'd multiply the two together and get that, in that example, of double parity at the erasure coding level, the distributed level, as well as double parity in the local RAID level. That would give you 64% usable, which is great. 4+2, standard erasure coding is roughly 67%. So you're in that same neighborhood, but instead of having 4+2 level of durability of maybe 5 or 6 nines, here with the double layer of durability and almost the same amount of usable capacity, you're up over 11 nines. So many orders of magnitude higher durability. We also have a design utility on our website. I invite everybody to go check out. Let me actually bring that up real quick, and it actually does some of these calculations so that you can see some of that math of what the overhead of building a cluster is. So here, let me share that. Yeah, this is an example with using our design utility. You can just go to osnexus.com, go to resources, go to solution design utilities tools here, and then you can go bring up the solution designer. You want the second one, the scale out solution designer, is for designing Ceph clusters. And here you can pick from a variety of different models that are all flash. Like here's an example, all flash super micro unit with 32 drives per chassis. These are great for using with xiNOR xiRAID. You've got plenty of slots to go and make multiple RAID groups with. And then you can just adjust the overall capacity. You can adjust which NVMe drive is in there. So you can say, I want to use 30 terabyte drives to go, build, say, a 4 petabyte cluster as an example. And down below, you can adjust the erasure coding here. This isn't going to add in the, calculate the xiNOR RAID capacity overhead. Again, if you were using 8+1, you would take this usable capacity that's coming out of this cluster and then reduce that by roughly 10%. But the design utility will give you some various performance numbers. And when you take a look at the performance of the xiRAID, it is getting you near line speed out of those drives. So the Ceph, basically, you can treat them as if from a performance perspective, as if the xiRAID wasn't even there. And so the numbers that you're getting here for performance are accurate. You can go and use these numbers as a way to still size your cluster in terms of overall performance. And then, to add in the xiRAID, again, you're just going to go and take a reduction of 10 or 20% on the usable capacity to go and add that layer. And again, your durability is going to go from 6 nines to 11 plus nines of durability, localizes all those rebuilds, eliminates the temporary peering stun, and your cluster is healthy all the time. And that's another one of these great benefits. There's certain operations like deep scrubs and things that pause when you've got backfills happening in your Ceph cluster. When you're using the double layer technique, that local rebuild is happening completely independent of your Ceph cluster. So it's able to do all the various maintenance operations of your Ceph cluster without interruption. So some huge benefits there. All right.
Awesome.
Well, go ahead. Yeah, sorry.
Oh yeah. Was that everything from your guys' side? Did you have any closing statements?
Go ahead, Dimitri, if you had anything you want.
Yeah, I think that what we demonstrate today, it's a good example how easy we can integrate xiRAID on QuantaStore a complete solution, and what it gives to the end customers, it's very easy way how it could be deployed. So you don't need to do any manual interactions, any installations of the kernel driver, and so on and so on. Everything you got out of OSNexus build, and it would be as easily deployed as you can do with standard OSNexus installations.
Yeah, really good point. And our global support team takes first call on everything. We take, and if there's an issue with the xiRAID, there is a direct linkage between the organizations for us to go and provide additional assistance there. So it's a great technique to leverage. Again, think about it anytime you're at scale, anytime you've got multiple sites, anytime you need that additional durability. We've done clusters where we've done this double layer durability anywhere, even starting at 400, 500 devices, we've started to use double layer durability. It all kind of depends on the environment and also, the time taken, right? It also saves on a huge amount of maintenance costs because going and replacing a drive in a RAID set, super low complexity versus having to think about how to go and do the same maintenance activity for your Ceph cluster. There's a way, with the separation of the layers to be able to go and very easily train people on, hey, here's how to go and deal with replacing a drive in the bad RAID set, super low complexity to go and maintain things that way.
Awesome. Well, thank you, Steve and Dimitri. I think OSNexus and Xinnor will both be at PERC next month in Minneapolis. So you can go to osnexus.com/PERC26. I'll put it in the webinar chat, and you could schedule a meeting with us or yeah, stop by our booth. So yeah, hope to see some of you there. But thanks for joining today, everyone. And yeah, have a good rest of your day.
Thanks, Lauren.
Yeah, bye.
Thank you. Bye
Thanks,
bye.
Dimitri.